How does sublimation lead directly to a gas state? Imagine a block of ice turning straight into water vapor without melting into liquid first. That's what we call sublimation, a fascinating process in the world of thermodynamics. When you see dry ice vanish in the air, it's sublimating directly from solid to gas. But how does this happen? Let's break it down. Matter exists in three main forms: solid, liquid, and gas. Usually, to go from solid to gas, a substance melts into liquid and then evaporates into gas. But sublimation skips the liquid stage entirely. This occurs under specific temperature and pressure conditions, usually below the substance's triple point, the exact point where solid, liquid, and gas phases can all coexist. During sublimation, the solid absorbs heat energy, which is an endothermic process. This energy makes the molecules move faster and faster. When enough energy is absorbed, molecules at the surface gain enough momentum to break free from the solid structure and escape directly into the gas phase. The amount of energy needed for this is called the heat or enthalpy of sublimation. It combines the energy required to melt the solid and then vaporize it, even though physically, the liquid phase is skipped. On a pressure-temperature diagram, the sublimation line separates the solid and gas phases. When conditions cross this line, sublimation happens. For example, dry ice, which is solid carbon dioxide, sublimates at atmospheric pressure because its triple point pressure is higher than the pressure of the surrounding air. You can see sublimation in action with snow or frost in cold, dry weather. Instead of melting into water, the ice slowly turns into water vapor and disappears. Freeze-drying food is another example. The frozen water in the food sublimates under low pressure, removing moisture without passing through the liquid stage. So, sublimation leads directly to a gas state because the solid absorbs enough energy to let its molecules escape straight into the gas phase. This process depends on the temperature, pressure, and the forces holding the molecules together in the solid. Understanding how sublimation works helps us explain natural phenomena and develop technologies that control phase changes.